Hi everyone. Before we get going, just a very quick announcement. I've noticed for the second lecture in a row that the software I'm using to record these lectures, software that UBC gives us called Camtasia, is experiencing a bug on Mac OS systems where the camera will occasionally freeze. That's the reason why in both the previous video and in this one today, you'll notice at one point my camera just drops out. My apologies about that, and I'm working with the tech support team to do my best to fix it. It does seem to be a software issue rather than a hardware one, and hopefully we'll figure out a solution for future lectures. Hope you enjoy this one. Hi everyone, this is the second out of two pre-recorded lectures for the Methods and Statistics chapter and the third pre-recorded lecture overall. So today we're going to wrap up our discussion of experimental methods and the corresponding chapter 2 in your textbook. Very briefly, in the last recording we talked about the idea that science, including psych, gathers knowledge through observation rather than intuition or authority, but we noted that there are many problems with using observation as the sole pure tool for knowledge, including that it's not always possible, reliable, or even true. There are disagreements and biases across different people, and psychology has extra issues because of the natural complexity, variability, and reactivity or demand characteristics of the sample that we're studying, human beings. And we talked about how to solve these problems, science gives us a variety of tools and rules. Last class, we talked about research questions, operational definitions, instruments, data, descriptive statistics. And today we're going to wrap up our discussion by talking about the various rules that psychologists follow when they are doing their science in order to especially get beyond the kinds of biases that might inflict us both when we are observing something and when we're making decisions from that observation. And the first set of rules that I want to talk about is a very specific set of rules that concern how we actually ask our questions. What kinds of questions are, in a sense, permissible within psychology? There's a couple of very important things to review here. One very important rule that psychologists really try very hard to stay true to is the concept of openness. That all of our data, all of our experiments should ideally be completely open to the public. And there's a major movement within psychology now that has been gaining steam over the last 10 years, where most psychology labs today publicly share all of their methods and data, preventing the possibility that by sort of restricting the tools that we are building and sort of isolating them into little research silos, that other people cannot use them. And more importantly, it allows other people to evaluate our tools in order to make sure that we can have proper disagreements about, is this valid, is this reliable, etc. The second major rule is that when psychologists are formulating hypotheses or predictions about what should happen given some observation of the world, these must be what we call falsifiable. It must be the case in confirmation and confirmatory studies that the predictions we're making must be inflexible and must be able to be shown to be false with observation alone. So what do I mean by that? Well, if we think about a particular hypothesis, let's say that we hypothesize that people who do well in PSYC102 are the people who do a lot of self-testing, then I need to formulate my hypothesis in a way where that can actually be shown to be false. That is, where I can say my hypothesis is therefore that, if I grab all the people who study with self-testing and grab all the students who don't, that the students who do should do better than the ones who shouldn't. Or alternatively, if the students who are doing a lot of self-testing do worse or do exactly the same as the ones who are not, then my prediction would be false. And throughout this course, you're going to encounter several times where we're actually going to be dealing with non-falsifiable hypotheses. Hypotheses where somebody claims that the explanation for a particular phenomena is something that just can't be observed. And that might be true, but ultimately if it is outside the purview of scientific psychology. And so we'll come back to the idea of falsifiable hypotheses again and again, but ultimately psychologists believe that the only things that we can study in the science of psychology are those that are observable and those that we can actually show to be false through observation alone. The third major principle is what we call double-blind experiments. Ideally, whenever possible, neither the participant nor the actual person collecting the data should be aware of what the hypothesis is. This can't always happen, and in a lot of psychology studies, it's not the case. But the hope is that by making participants blind, we are ultimately blind to the hypothesis. That is, we are removing demand characteristics. And by making the experimenter or the person collecting the data blind so that they don't know what the hypothesis is, that they can't exert undue influence on what it is that they're observing. They can't, make decisions that what the participant did is actually consistent with the hypothesis, even when it's not. And the final major rule concerns the ethical treatment of participants in data. Data must be acquired in a manner that's fair, not faked, plagiarized, or altered in any way. And I'll say this, we will not talk more about ethics in today's lecture, but your textbook has a number of really important subsections on ethics that you absolutely are responsible for and that we will test a lot throughout this term. So please make sure that you read about ethics from your textbook. This part's going to be important, even though I'm not going to talk about it any further today. Now, in the second major section that we're going to discuss today, I want to talk about particular rules for how we collect our data, principles that we follow when data is being collected, and what we are allowed to conclude based on how we collected the data. This is something we call experimental design, also sometimes just known as experimental methods. These are sets of rules and procedures that we use to gather data. And today we're going to learn about 4 of them, each with their own distinct sets of pros and cons. So we're going to learn first about naturalistic observation, then about case studies, correlational studies, and finally about experiments. So let's first talk about naturalistic observation as a method for collecting data. Naturalistic observation is when you observe your participants in their natural habitat, in the wild, so to speak. And you will observe them and write down various behaviors and try to make inferences about what's causing their behavior or what they are doing. Much of the time, naturalistic observation is actually going to collect qualitative data because it's going to be a description of what a person is doing, though not exclusively. One can also say, come up with a particular scale where you count the number of times a particular participant did something and therefore make it quantitative. But naturalistic observation most often leads to qualitative data. Naturalistic observation is often also done secretly. So the two most common places where we do naturalistic observation can be, for example, in schools, where we might observe children on a playground or something like that. Or alternatively, it can be in situations like Facebook. So Facebook, to I hope none of your surprise, sells your data. That's how they make most of their money. And researchers very frequently purchase that data and analyze it for various kinds of patterns, like, how often you post and how that relates to various aspects of your social network. And so as a result of that, very often what we do is we do naturalistic observation where your data that you're generating on social media is being observed to some degree by psychologists buying that data, and that it would count as naturalistic observation. Now, there's a couple of really important benefits of doing naturalistic observation. One is that because most of the time we can do it secretly, participants don't know that they're actually being observed. I mean, if you read your sort of terms of conditions of Facebook, you'll notice there that, oh yeah, of course, they're saying that, the privacy of your data is really not all that high. But nevertheless, the hope is that because you don't know that you're being watched, you're behaving naturally, and demand characteristics are low. The other reason why naturalistic observation is good is because it has very high what we call external validity. External validity is the question of how much can I generalize from your behavior to the rest of the population. And usually the problem in a lot of experiments is that when we bring people into the lab and make them do these really artificial tasks that, have no resemblance to real life, then we have to wonder how much is anything that I find when I put you in an artificial situation true in the real world. But in naturalistic observation, I'm watching you in the real world. And as a result of that, I can have pretty high confidence that the behaviors I'm observing are actual behaviors that people do in their day-to-day life. But despite these pros, there's a number of really major cons. One big one, and one that you're going to see recurring again and again, is that we can't actually tell from naturalistic observation what caused a particular behavior that we're measuring or observing. Suppose you're watching a couple of kids on the playground because you're interested in the way in which, food consumption is maybe related to bullying behavior. Like you're wondering whether the kids who are coming to school and, not eating their lunch, are they sort of bullying other kids more? So, you're watching kids during lunch hour, you find that a bunch of kids are not eating their lunch, and then you later observe those same kids bullying. The problem here is that you cannot make the inference that it's actually the lack of eating lunch that caused that bullying behavior. Because for all the things that you've observed, there's a million others that you didn't. You don't know what those children's home environment is. You don't know what those children's past history is. You don't know if those children have bullied, kids before and after. So it's really hard. In fact, it is impossible to know for sure why the behavior that you're looking at is happening. And because in sciences, we most often do care about causality, we're trying to build explanations of why behaviors happen, naturalistic observation is not going to get us there. In addition, for most participants, with the exception of things like social networks or situations where we can get permission from the parent, most of the time we ethically do have to tell participants that they're being watched. And as a result of that, we can just reintroduce the main characteristics, And finally, the last major problem is that naturalistic observation is very prone to experimenter bias because somebody has to watch and make decisions about what to record and how to record it. And as a result of that, it's very, very hard to avoid the fact that me as an observer, that I'm also interpreting what I am watching. And as a result of that, that problem of my undue, sometimes conscious or unconscious biases can creep into the data. The second major experimental method is what we call case studies. This is a situation in which I find a very unique individual, and I observe their daily behavior or their behavior on a series of tests that I devise in order to see how that unique individual behaves. This happens very often in psychology, for example, when we find individuals who've either had a very unique lived-in experience, for example, people who maybe grew up without any language exposure, or in situations where a participant maybe had a very unique stroke that caused damage in a very specific brain region. And we're interested in how damage to that specific brain region leads to changes in behavior. The pros of this is that most of the time in most of our experiments, we're going to collect massive samples of participants. And as a result of that, a lot of individual differences, a lot of uniqueness between people is sort of going to be washed out. Case studies allow us to find those unique individuals and go beyond the average, figuring out how some very unique individual behaves in a range of situations. This is especially useful for falsifying hypotheses. This is sometimes known as the black swan principle, the idea that if you have a hypothesis that all swans are white, it takes just single black swan to falsify that theory. And likewise in psychology, we often have theories that say that all X's are Y's. And case studies are the perfect example of we just need to find one person who doesn't follow that rule, whose psychology doesn't follow that principle to falsify the entire theory. So they're very useful for that. But just like with naturalistic observation, we don't know exactly what's causing the behavior. Maybe it's the brain damage and brain damage alone. Maybe it's the fact, that it's this specific thing that makes the participant unique. But I can never know if it's just that. There could always be additional things that make this person unique that are unrelated to the thing that I think is causing the behavior that might be causing it instead. And in addition, the main characteristics are always high. The case study participant, by definition, knows that they're being observed for a very specific psychological experiment. And so we always have to wrestle with that. Now, case studies and naturalistic observation are used sometimes in psychology, but they're relatively rare. But by far, what is the most common method are the next two we're going to talk about, and especially correlations. A correlation is a measurement of the relationship or the predictive relationship between two variables or data sets. In other words, what a correlation tells us is, if I know something about one variable, how much can I predict something about another? Let me make this very concrete. For example, I could wonder whether there's any relationship between the amount of sleep you get the night before a midterm and how well you perform on that midterm, right? Maybe that's something you yourselves care about a lot as well. So if I were to do a correlational experiment, or a correlational study, what I would be doing is asking, well, if I know how many hours you slept the night before, how well can I predict how well you'll do on a midterm? How much predictive relationship is there between sleep and midterm performance? Or if you don't like that example, consider, if I know how old you are, how well can I predict what political party you'll vote for? Or if I know that you are very social as a person, how well can I predict how many friends you have on Facebook? These kinds of questions are the bread and butter of psychology. And correlational studies are still, to this day, the most common type of study that psychologists do. This is, by the way, also true in political science and economics and many other what sometimes people call soft sciences. Correlational research is just ubiquitous. Part of the reason why that is because to do a correlational study is generally pretty straightforward. You begin by choosing two variables you're interested in. Let's say hours of spent sleeping before a midterm and the percentage correct on a midterm. You then just have to find good instruments for measuring both. You then measure them with as many different people as you can. You will then graph the relationship, putting one variable, let's say amount of sleep, on the y-axis, and another variable, let's say midterm performance on the x. And then you will estimate the direction and the strength of the correlation. Let's visualize this to make it really clear what we're talking about. So here what I've done is I've put up a graph where we're mapping the hours of sleep on the x-axis, the horizontal one, and the percentage on the midterm on the y-axis, the vertical one. And suppose that we, collect data from 300 different students. For every student, we get a measurement. How many hours did you sleep? How well did you do on the midterm? And if we graph the data, we might get something like this. In this particular graph, each individual point is an individual participant. And so there are some participants you can see, if I just, hopefully you can see my mouse, like this participant right here. They got a 60 on the midterm and they slept for around 11 hours the night before. It seems like an absurdly high number of hours to sleep. I'm very jealous of that person, but hey, this person right here, right, got somewhere just above 40% and they only slept an hour, right? And the point here is that from this measurement, we can now infer the direction and the strength. The direction of this relationship is something known as a positive correlation. These two variables positively predict each other. The people who slept more generally tend to do better on the midterm. If I know how many hours you slept, I can't perfectly predict how well you'll do on a midterm. If I pick all of these people who slept 5 hours, we see there's a range there, but I can tell that on average, people who are sleeping 5 hours are doing worse than people who are sleeping for 10. This is what we call a positive correlation. Now, in addition, you can estimate what is known as the strength of the correlation. The tighter these dots are together, the stronger the relationship is. Though I will tell you right now that in this course, you do need to be able to understand how to interpret the direction of a correlation, but I will not be asking you about the strength of it, though your textbook is going to go through some of that. Ultimately, you can largely ignore it. This isn't the only direction of a relationship we might find. For example, it's also possible that maybe we'll find a negative correlation. A negative correlation doesn't mean that there is no correlation. It just means that the more I have of one variable, the less I have of another. So unlike the positive correlation here, what we see is that on average, the more people have slept, the worse they're doing on a midterm, right? So people with more sleep have lower grades. That's what a negative correlation is. And the final possible pattern I could find is that there is no correlation. There is no relationship at all. People who slept on average 2 hours don't do any better or worse on average than those who slept for 12. The line is flat, no relationship at all. So as psychologists, this is a lot of what we do. We find excellent instruments, measure people on a host of different variables, and try to ask, if I know something about one variable, how well can I predict another? Now, this might convince you that, great, correlations are so easy. They're awesome. They're relatively cheap to do because you just get people to do a bunch of questionnaires. They're fast to do. You can just get people to do a whole ton of questionnaires online or in person or whatever. You might sort of say, great job, psych, you did it, right? What else do we need to do? There's a problem here. And it is a problem that is so big that I'm going to sort of really hit you over the head with it. Then I'm going to hit you over the head with it some more. Then next class, I'm going to remind you of it again. Then the class after that, I'm going to remind you of it again. And I'm going to, after this class is over, I'm going to randomly at one point in your undergrad email you and remind you again because it is that important, okay? And the problem is that a correlation between two variables does not imply that one variable caused the other. This is an illusion that is so powerful that there are many psychologists who believe that our minds are programmed to think about correlations wrong, that this is a kind of an illusion that humans need to actively fight against. So let me say it again then. A correlation between two variables does not imply that one caused the other. And you might wonder, well, surely it tells you a little. No, it doesn't. It tells you absolutely nothing. It doesn't tell you if a variable caused it or if it did not cause it. And so now you might wonder, why is that? If I found that people who on average sleep 2 hours are doing worse than people who slept 10 hours, then how could it possibly be the case that sleep did not necessarily cause midterm performance? Well, there's two reasons why. The first is what we call the directionality problem. For any given correlation, you can never know whether variable A caused variable B or if B caused A. I plotted that graph with sleep on the x-axis, but that's completely arbitrary. I could have put midterm performance on there. So yes, maybe sleep is causing better midterm performance because more rested people do better on a test. But maybe, maybe this is the direction of the correlation. But maybe on the other hand, it's actually people who are going to do well on the midterm, who are super relaxed the night before, and they just end up sleeping well. And they would have done well on the midterm no matter what. But having known I'm going to do great, they just ended up being very relaxed and able to sleep the whole night rather than cramming last minute. So the truth of the matter is, the moment I point this out to you, it sort of becomes intuitive that the direction could have been either way. But the illusion is really strong. And much of the time when you hear a correlation, your mind will naturally jump at trying to make these relationships even when they're not there. There's an even bigger problem than the directionality problem, and that is known as the third variable problem. For any given correlation, there could be a third, completely unmeasured variable that is actually causing both of the other variables and creating what seems like a causal relationship between them when they have no causation at all. So for example, maybe sleep causes better midterm performance. Or maybe there's a third variable, something like whether you have a cold, are you sick, which is ultimately going to make you sleep less and do worse on a midterm because you can't concentrate. In this case, you're still going to find a correlation between sleep and midterm because people who are sleeping less are also the ones who most likely have a cold. But it has nothing to do causally between sleep and midterm performance. If this example is a little too, dense or kind of silly, consider the following. There is an extremely good positive correlation between how much ice cream people consume and how many people get attacked by sharks. Now, even though I just told you all of this stuff about directionality, right, and third variable, your mind is probably still kind of buzzing, being like, that's weird, right? Like, do sharks get attracted to people who just ate ice cream? And of course, no, not at all. There's a third variable here. It's summertime, right? People generally are in the ocean where they're more likely to get attacked by sharks when it's warm outside in the summer, and people are more likely to eat ice cream in the summer. There is no causal relationship between ice cream consumption and shark attacks, but there's a very strong correlation between them because of a third variable impacting them both. Now, this kind of a problem of interpreting correlations as causal is incredibly common, and at times also kind of incredibly hilarious. There's this website that I actually encourage you to check out. It's a website where a person graphs relationships that are incredibly strong correlations, but that are completely what we call spurious, where we know there's no causal relationship there. One of my favorite ones and one of the most famous spurious correlations, there is an extremely strong correlation between the number of people who drown by falling into a pool every year and the number of movies that Nicolas Cage appeared in that year. This correlation, this is an extremely strong correlation. This is the kind of correlation that, like, if you're a psychologist and you actually observe a correlation of the strength in your data, you think your career is set for life, okay? And again, your mind might be wondering, like, why is this, right? Like, do people really hate Nicolas Cage movies and, go drown themselves in a pool or something? No, of course not. In this case, it's a complete coincidence. But nevertheless, it's an extremely strong correlation. And in this case, this is sort of an example in which your mind would hopefully naturally resist the causal interpretation. But for many, many, many other situations, your mind will absolutely jump at the causal explanation. Mistaking correlation and causation is incredibly common and serious, even for trained professionals. I still, at a regular basis, despite knowing this, sometimes read about a correlation and instantly start thinking that it's causal. And nowhere is this a bigger problem than in the media. I want to share with you 4 headlines from major news sources, reputable news sources, in which the article is claiming a causal relationship from something that is just a correlation. Lack of sleep may shrink your brain, right? Very provocative title. From a study that found that people who are sleeping less also have smaller brain volumes. Now, this might sound very plausible to you. There's a reason why this headline was written this way. Wow, a lack of sleep really causing some damage to my brain. Or maybe there's a third variable here. Maybe the people who have brain damage or some kind of, early dementia are losing brain volume and as a result of that also sleeping less. Or consider diet of fish can prevent teen violence, right? New study reveals root cause of crime may be biological, not social. Or maybe it's the case that, families who have access to fish as a source of nutrition are in some way different from those who don't. Maybe it is, generally very poor neighborhoods that have a lot of food deserts, that have lack of economic opportunities that leads many people into violent behavior, and also don't have access to, fish and other kinds of groceries. Or consider, want to live longer, even if you're poor? Then move to a big city in California. This is a correlational study that demonstrated a correlation between life expectancy and living in a big city in California. This, by the way, is from Ezra Klein, who, again, proof is in the pudding that even highly educated, smart people who generally are very cautious about correlation and causation sometimes fall for it. Because does living in a big city in California make you live longer? Almost certainly not. But it's definitely the case that the people who live longer are generally wealthier, and they are also the ones who tend to be able to naturally afford to live in a big city in California. Or consider sugar rush to prison. Study says lots of candy could lead to violence. This is a study that demonstrated that sugar content is related to violence. I mean, this study is, again, most likely just because of issues such as food deserts inducing a correlation, not because the presence of sugar in your body makes you commit crime. I mean, that's absurd. We would have a crime spree every Halloween, right? That would just be outrageous if this was actually a causal relationship. So mistaking correlation for causation is incredibly common. And the problem here is that so far we've talked about 3 different experimental methods: naturalistic observation, case studies, and correlations, none of which allow us to actually conclusively say if one variable caused another. Luckily, we're not stuck there. And the last experimental method we'll talk about is something known as experiments. Now, in our sort of regular, everyday conceptualization of science, everything a scientist does is an experiment. The truth of the matter is that experiments, though, have a very specific meaning. They're a very specific procedure for gathering data, where one variable is what we call manipulated or changed, and I'll explain what this means in a second, in order to see if it carries a causal effect on another variable. So in this class, when I use the word experiment, I'm talking about a very particular type of scientific design. And in general, you're going to hear me use the word study as a more general term for any, scientific endeavor where we're trying to collect some data. So we'll try to do experimental studies as a very specific example of a particular method, as opposed to correlational studies or natural observation studies, etc. Because it would ultimately not make a lot of sense to call something a correlational experiment, right? So, how do experiments work? Well, if I wanted to know if there's an actual causal relationship between amount of sleep and performance in a midterm, I could ask some people to stay awake all night, then do the midterm, while others are allowed to get a lot of sleep and then do the midterm. And as I'm going to show you in just a little bit, what we've done here is we have manipulated the amount of sleep. We've forced some people to sleep a lot, we've forced some people to sleep not at all, and then we're seeing what is the effect of that on the measure of interest. Or alternatively, so the point here is that if sleep causes better midterm performance, then these groups will do differently. People who slept more should do better, and people who were forced to sleep less are going to do worse. But if the only reason why that correlation existed was because of the third variable of being sick, then it won't matter how much sleep I force upon somebody, right? Because if being sick is the only reason why someone does better on a midterm, then if I change the amount of sleep they're getting, it ain't making a difference in the world for the midterm performance, right? Or alternatively, if you prefer a different example, we could ask some teenagers to eat a lot of fish, feed them sushi every single day. Others no. And we could see how many people they murder, right? Of course, we can't actually do that, not ethically. And I hope that, again, just as a good reminder, read your ethics section of the textbook if you are wondering why that's not ethical, or what kinds of studies would be in this instance. But that's the point. If we think something is actually causal, we manipulate it, give a lot of it to some, give none of it to others, and see if it actually carries a consequence on an outcome. So an experiment is fundamentally made up of 4 components. You need all 4 of these. If you lack any of them, it is not an experiment, or it's a really bad experiment, and causation goes back out the window. The first component is what we call an independent variable. This is the variable that we're actually manipulating during the experiment, like hours of sleep, or amount of candy that I'm feeding people, or amount of fish, or etc., or where I'm forcing people to live. Whatever it is that I'm manipulating, a lot to some, very little to others, that's an independent variable. The other component is the dependent variable. What am I measuring? What is the thing that I think there might be a causal impact on? So this would be performance in a midterm, or crime rate, or murder rate, or life longevity, or whatever else. So the independent variable I change, and then I measure how do changes in the independent variable change what the outcome is on the dependent variable. The third major component is what we call random assignment. That means that when a participant comes into the lab to do my experiment, they are put into an experimental group randomly. In other words, every single participant is randomly assigned to, let's say, the low sleep or the high sleep condition. I don't allow something like, you come into my lab, I ask you, are you naturally a night owl? And you say yes, and I'm like, great, then you're going to go into the low sleep condition. Or I don't allow you to come into the lab and say, are you sick? You're sick? You should get a lot of sleep. Go get a lot of sleep. No, completely random. And the importance of this we're going to reveal in just a little bit. But any person must have an equal chance of being in any one of your levels or groups of your independent variable. And finally, there's something known as random selection. The participants that you actually bring into your lab for research and then randomly assign must be a random representation of the general population. I can't only recruit, men under the age of 18 for my study if I want to get a study that is really about the whole population. So I, of course, can't test the entire population. I have to sample some number of them, but ideally it should be random. And it may not be obvious yet, but these 4 components do allow you to infer causality. So why? Well, remember, there's 2 problems for why we can't infer causality from correlations. One is a directionality problem. I don't know if A caused B or if B caused A. Well, in experiments, I do. Because I specifically controlled for one. I specifically manipulated one variable to see if it has any kind of impact on the other. I chose to manipulate sleep to see if sleep has an impact on midterm performance. If, on the other hand, people who know a lot more of the material are just going to do better, and they would on their own just sleep more, then me making some people sleep more versus less ain't going to make a difference. If you were confident, it wouldn't matter whether you were going to sleep a lot or little. There's not going to be an impact on that. So directionality is solved because I choose the direction to test by manipulating one, the independent variable, and measuring the other, the dependent variable. The third variable solution, the possibility that there could be all kinds of hundreds of others unmeasured variables that could be affecting both of them, is controlled with random assignment and random sampling. The idea is that if we really truly randomly selected our participants from the population and randomly assigned them into different independent variables that we've created, then given enough participants, the 2 groups should be equal in every regard except for the manipulated variable. So suppose that maybe sleep and midterm performance are really strongly affected by whether you're sick. I'm not testing that in my experiment, but if I am truly randomly bringing people from the general population and randomly assigning them to the 2 conditions, then I'm going to get an equal number of sick people in both my high sleep and my low sleep condition. And if sleep has nothing to do with midterm performance, if it's all about sickness, well, the 2 groups are equal on their level of sickness, and that means that sleep is not going to produce a difference on midterm performance. If, on the other hand, sleep is really what matters, then even though we have an equal number of sick and not sick people, equal number of night owls and non-night owls, equal people of confident and non-confident people, if sleep is causal, then when I change sleep, it should lead to a change in midterm performance. So the idea is that it's that sampling and assignment that allows us to conquer the third variable problem. And so because experiments solve directionality in third variable by choosing the direction and randomly getting people so that our groups are identical except for the variable we're manipulating, they can tell us if one variable is causing another. In fact, experiments are the only way to do so conclusively. And so ideally, most of our studies, when we care about causality, they need to be experiments. Otherwise, we can't make causal claims. All right. In the last 10 minutes, I'm going to switch into the final topic we're going to talk about. So today, to sort of take a moment, we began by talking a number of different rules for how questions are asked: openness, ethics, falsifiability, double-blind experiments. Then we talked about rules for how we collect data. We talked about different methods. naturalistic observation, case studies, correlations, experiments. And the final set of rules we'll talk about is what do we do with the data once we've collected it? How do we make decisions in a way with our data to avoid the kinds of biases and issues with complexity, etc. So last class, we talked about something known as descriptive statistics, tools for describing data, like the typical value with the median and the variety of data with the standard deviation. Inferential statistics are the other side of the coin. These are mathematical tools that help us make unbiased decisions about what the data means. Descriptive statistics describe data. Inferential statistics tell us what kinds of conclusions are justified given the data. Now, I want to know one very important thing. Inferential statistics do not make decisions for us. They just help us make decisions. A lot of times people are very distrustful of inferential statistics. They sort of say that they can be manipulated, don't trust statistics. Well, they can be manipulated just like any other tool can be manipulated. No tool is inherently good or bad, right? A hammer is needed to build a house, but you can also do a lot of horrible things with a hammer as well. Likewise, inferential statistics are truly a boon for our ability to make better decisions with data. But of course they can be misused as well. But there's nothing inherently negative about them. So I want to really try and release you from that worry that statistics are somehow inherently tools of liars, right? Okay, so let me give you a very concrete example to really make inferential statistics as clear as possible. Imagine that you have a friend who proudly runs up to you one day and says they just discovered that they have a supernatural power. You can flip a coin in complete secrecy, and they can guess whether it came up heads or tails. It's not a great superpower, right? Like they're like Coin Man or whatever, but it's still pretty cool because it maybe suggests that there is such a thing as like psychic powers out there. So here's the question I have for you, and I want you to think about this. How many times would your friend need to guess correctly for you to believe them? 1 time, 50 times, 100 times, 1,000 times. When I do this in class, there's an enormous range of values. Everybody agrees that 1 is too few, right? Most people say that 10 is probably still too few. But there are many people who think that, look, if my friend guessed 20 of them in a row, I'd say they're probably Coin Man or whatever. And there are other people who are like, nope, I need like 1,000. I need like 1,000 different guesses before I'm there. So how are we supposed to decide how much data is enough? Or consider another problem. What if your friend is doing 1,000 flips and eventually they're just a little tired? There's a momentary lapse of attention and they get one wrong. How many mistakes are they allowed to make for you to continue believing them? Because nobody's perfect, right? If I were to ask you to stand in front of the whole classroom and read a paragraph, you're probably going to stumble on a word. That doesn't mean you don't know how to read. But how do we decide these questions? How do we decide how many trials is enough? How many is too many? How many mistakes are okay? How many mistakes are too many? So here's the problem that we're faced. When we're measuring the behavior of any person, we got 2 problems. People can sometimes get lucky. They can do things based on luck alone and we can from that incorrectly conclude that they have some crazy ability. But people can also sometimes make mistakes. And as a result of that, if you think about it, at the extremes, as psychologists observing data, we can make 2 types of mistakes. One is what we call a false alarm. A false alarm is when we accept an event that occurred by chance as meaningful. That is, saying that your friend is psychic when in fact they just got really lucky. That would be a false alarm. But we can also make a different kind of mistake. It's what we call a miss. It's when there is a real effect out there in the world. Your friend is really psychic. But we reject it because maybe they made a mistake or we were way too overly conservative about how many trials it needed. So here is the important thing for you to take away. Inferential statistics help us decide what is the perfect balance between false alarms, accepting chance, and misses rejecting real effects. We don't have to rely on your or my intuition about whether 1,000 trials is too many or too few. Inferential statistics can help us make a criterion that we can all agree on is the right one, and therefore allow us to balance between false alarms and misses. Now, how inferential statistics do this is really complicated. And ultimately, I don't want to go into too much detail on it. I'm going to give you the briefest glimpse into it. And remember, ultimately, you don't need to know any numbers or anything like that. I just want you to understand it intuitively. So inferential statistics first begin by letting us specify what would performance look like by chance alone. We begin with what is sometimes known as the null hypothesis. We assume that the effect doesn't exist. And so we assume, let's begin with the assumption that your friend isn't psychic. How many trials should they get by chance alone? Well, if a coin is truly fair, then it's a 50-50 whether it'll come heads or tails, and we can create what is known as a probability distribution. What is the probability? What's the probability that your friend should guess 30 of them out of 60, or 60 out of 60, or 53 out of 60? And if you look at this graph, it makes a lot of sense. Because chance is 50-50, we should expect on average your friend most of the time to guess 30 of them right, if they don't have psychic powers, if it's chance alone. But it's not that unusual for them to guess, 29 or 31. It's not even that unusual for them to guess, 36 or something like that. It's going to happen by chance alone. So where do we draw the line? Well, in inferential statistics, we use something known as statistical significance. This is the boundary of probability at which we decide that if we observe a data point that is at this boundary, then it is unlikely to have come from chance alone. And therefore, we should consider that maybe something else is going on. In psychology, the critical boundary of statistical significance is most often 5%. If we observe an event that our probability distribution tells us is 5% or less to occur by chance alone, or by our null distribution, which most often is chance alone, then we say, okay, maybe something else is going on here. Notice this doesn't mean that it wasn't by chance. After all, at least 5% of the time, your friend will get lucky enough to guess that many by chance alone. But we need some boundary, and 5% is most often it. And we hope that then upon repeated testing, somebody who got lucky once at 5% will not get lucky again unless the effect is real. So again, just to make it a little bit concrete, if there were 60 coin flips and we only cared about positive guesses, not negative guesses, we would say that the 5% threshold is somewhere right around 38 flips. If your friend guessed 38 or 39 out of 60, that would be quite unusual given chance alone. And a psychologist's interest would sort of be momentarily perked up as they would say, maybe this is the first out of many experiments that I'm now going to see, or unnatural observations or whatever else, that are ultimately going to continue getting me data that might say that there is something really about being coin man or whatever. So that's all dramatically simplified. If you actually go into psychology as a major, you will have to take a course in some very basic elementary descriptive and inferential statistics. It's called PSYC102, where you will go into this in a lot more detail. But for now, all I really need you to know is that inferential statistics is what helps us to figure out what is that balance point between not making too many false alarms while not making too many misses. All right, so how does psychology solve the problems of pure observation? We said observation is not always possible, precise, or true, so we create good operational definitions and valid, reliable, and powerful instruments. We trust those even when, our eyes might be deceiving us, so to speak. Disagreements and biases that people inherently have and bring into psychology, just like they do everywhere else, we solve by keeping science open, by keeping it double blind, by keeping it ethical, and by randomly sampling and using inferential statistics to help us tell what's real versus not, instead of just, well, that sounds real to me, or something like that. And how do we solve the unique problems of studying human behavior, complexity, variability, and reactivity? Well, Complexity is solved by doing a lot of work, by making as simple a hypothesis as we can and building them together into ever-increasing theories, kind of like we do in other sciences as well. Variability, the fact that people behave very differently, we do by getting very large random samples of data, trying to capture as much of the variability as possible. And reactivity, we deal with by removing double domain characteristics with things like double-blind experiments, naturalistic observation when possible, etc. So that's it for this week. The next lecture will be on intelligence. I also want to remind you that at this point, you should have, if you've done your readings, everything you need in order to do your online quiz number 1 on Canvas. So it's due the following Monday. So Monday next week at 11:59 p.m. It's on Canvas. It's open book. It has 15 questions, a mixture of multiple choice and fill in the blanks. You'll have 15 minutes once you start to do it. So if you're choosing to do weekly quizzes or try this one and see how you do before committing to, doing some and not others or whatever, please remember to do that as well. Thanks a lot, everyone. Enjoy your weekend. And next time we chat, we'll chat about intelligence.